Okay, so our next speaker is Ivan Tomasic. He will talk about topos-theoretic view on difference algebra.
Thank you very much to the organizers. It's a pleasure to be here. So I would like to propose a rather new approach to difference algebra. I will start from the usual classical Enriched style approach and set up some framework of categories of difference objects. And then I will guide you through my steps to enlightenment on trying to develop cohomology in difference algebra. I promised in the abstract to give a solid foundation for difference algebraic geometry, and then I will finish with, time permitting, with some concrete calculations on cohomology of difference algebraic groups. So, okay, so how did Enriched define algebra of rings and modules with operators? Well, he said these are rings and modules with superimposed operators on top of them. Okay, so you start with a classical object, and then you add some, say, endomorphism in the case of difference algebra. So we're going to do this with an arbitrary category. So C is an arbitrary category, and you define the associated difference category, which has objects which are pairs x sigma, where x is an object of the original category, and sigma is just an endomorphism of x. And of course, a morphism between two such pairs is a commutative diagram which looks like this, or in other words, it's just a morphism of the original category which commutes with difference operators. So this is very classical. Although I can now do this for an arbitrary category. Now, it's very important for us to have a slightly different point of view, where I can view the difference category as a functor category in the following way. So I will define a very small category sigma, which is the category associated with the monoid n plus. It has a single object O, and the endomorphisms of O are the same as n. In other words, they're generated by a single endomorphism. In other words, the action of 1 in n. Okay, then I claim that the difference category, as defined on the previous slide, is the functor category of functors from sigma to C. The objects are simply functors from sigma to C, and morphisms are natural transformations. How do you get the translation mechanism from one side to the other? Well, if you take a functor from this category sigma to C, then when you evaluate it, you get a set, and when you evaluate it on the action of 1, you get a self-map, so that gives you an object of the difference category. Okay? The other way is also very easy.
But could it happen that now I have multiple distinguished endomorphisms associated with the same object?
You could do. You could. Sorry? Oh no. No. It's so you get sorry. I mean the higher ones. 2 is just the composite of this one with itself. The image of 3 is just a third power of sigma. It's
Yeah, but what if I will have another functor from sigma to C that has the same first coordinate but different second coordinate?
That's fine.
It's a function, so
That's fine. That's okay.
Ah, I see. Okay.
I mean, each functor gives a different set. Each functor gives rise to another difference object.
I think what he might be asking is that instead of this little sigma being a single object, maybe it has two objects.
You could. Well, you
And
could.
then,
You
you know,
could. We could discuss. So this can all be generalized to actions of an arbitrary monoid.
That's right.
All right. So
You went back.
I went back. Okay. So for people with experience in categorical logic, there's yet another way of viewing the difference category, which is, so you define the algebraic theory of a single endomorphism.
What does that mean?
That's just a theory with a single object for a function and no relations.
So it's first order theory. What is it?
It's a kind of first order theory, but in the categorical setup. So it's just a first order theory with a symbol for a function, but no axioms whatsoever. And the category of models of that is the same as sigma c.
The category of models. So what?
Of this, so a model
What is-
just has to have a realization.
What is C?
Any category.
C is an arbitrary category.
Oh.
So the
Oh, the
category
ca-
of
oh,
models
oh.
in an arbitrary category
Is
is the
okay.
category of sigma objects.
Okay.
Yeah.
Category of models in.
So it's not a model theory.
Models of S in.
Yeah.
Yeah, I know.
Yeah.
In fact, what?
Your life in the past.
No, in fact, I did I've got to confess that about a year ago and a half, I taught a course in categorical logic in Notre Dame.
Yes.
Tapas course.
So I'm trying now to convince you that it was worthwhile.
No, I ended up with opposite conclusion. I'm serious. I did the opposite.
Okay. All right. So I went back again. Okay. So examples that will be relevant for this talk include different sets, different groups, which are different sets are just sets with a self map. Different groups are groups with a self homomorphism or endomorphism. Different rings, again, just rings with an endomorphism with no assumptions. And of course, given a difference ring R, you can also consider the category of difference R modules. Unfortunately, it's not a sigma of another category because there's a non-trivial action of sigma on R. This can be dealt with, it's not a problem, but I don't want to waste time doing it. It'll become clear later how this fits into, but we can treat that as well. Oh.
R module means R. Different.
So R modules are difference R modules for a difference ring R. I have this convention, I don't write the sigmas. If I want to, so if I have R, then if I want to say sigma ring, if I want to talk about the underlying ring, I will denote it like this. Okay, so that's my underlying ordinary object.
So your RNG has no identity.
R does have a non-trivial sigma on it.
No, but does it has an identity, the ring itself?
Oh, yes, yes. Yeah, okay. These are, say, commutative modules with identity, yeah. Okay, so, all right, so I would like to now guide you step by step through the levels of conceptual steps that led me to how to develop cohomology in this context. So I'd like to develop homological algebra of difference abelian groups and difference modules, and then later give also a solid foundation for difference algebraic geometry. When you look at any book on homological algebra, you realize that homological algebra is based on certain key identities and dualities. And I chose two examples here. So in set, you have this currying isomorphism, which mathematicians are not really excited about. It's just clear. But computer scientists are crazy about this. They have this Curry-Howard correspondence. Anyway, so then if you take a normal ring, then the Hom set of modules is also a module for the same ring, and you have the familiar Hom tensor duality. So this makes sense because this is also an R module. All right, let's see what happens in difference algebra. So in difference sets, if you look at only those maps which commute with difference operators, this is just a set. It doesn't have an action of sigma. Even if you might think, let's impose some artificial action of sigma on it, but it will still be too small to satisfy the identity. For rings, it's also very bad. Again, if you look at difference R module homomorphisms, again, it doesn't have a structure of a difference R module. It's the best you can say is maybe that it's a module over the fixed ring of R. So Hom tensor duality badly fails. And again, if you try to impose some difference operator here, this will be way too small to make it work. So that's our awakening step. Something wrong, something very wrong. Okay, then you rumble through category theory literature, and you come across the definition of monoidal closed categories. So symmetric monoidal category V is closed when, for any two objects B and C, you have internal Hom objects. So these are not Hom sets, like in usual category theory, but this is, again, an object of the same category, and this object fixes the problem with Hom tensor duality. Okay? And we say that a category is Cartesian closed when it's monoidal closed for the Cartesian product structure. Now, okay, with the obvious attempts for the Hom objects, it didn't work, but perhaps there are some less obvious internal Homs that will make our desired categories into monoidal closed categories.
What is symmetric here?
Symmetric means that the tensor x tensor y is canonically isomorphic to y tensor x.
It's a tensor category with what?
It's a tensor category
plus
identity for the tensor structure plus this and well, lots of axioms, associativity of the tensor product and so on and so forth. So, okay, there's another notion of enriched categories. So once you have a symmetric monoidal category, as defined just now, you can talk about a V category or a category enriched in V, which consists of a class of objects, and then for any two objects, you have, instead of Hom set, as it would be in a normal category, you have an Hom object, which is an object of V. Now, of course, you can't really talk about an arrow between X and Y, because it may be forbidden to talk about elements of this. This may be a non-concrete category, so you may not be able to talk about a single morphism from X to Y. So the properties of composition and identity have to be stated diagrammatically. So the composition is going to be a V morphism, some abstract thing, and identity is going to be given by this unit morphism, and they will satisfy the expected conditions, but they have to be stated through commutative diagrams. Now, as you already noted, a V category is not a category necessarily. However, there is a notion of the underlying ordinary category. So, if V is as before, you have the points functor or the global section functor from V to set, which just takes Hom identity X, and that's a set. So for a V category C, you can create the underlying category C0, which has the same objects, and then for two objects X and Y, C0 of XY is the set gamma CXY. So CXY is an object of V, but gamma of that is a set. Now, this is a very forgetful operation. It forgets a huge amount of structure. So enriched category theory is very well developed and well understood. For example, if you take two enriched categories, then the functor category is also an enriched category. And you can talk about enriched presheaves, enriched Ionada lemma, and all this. However, what I couldn't find in the literature, a suitable context for developing homological algebra, so I kind of came up with some notions here. Basically, the issue was, usually when you have some functors between abelian categories and you derive them, you get functors. But here I have some enriched functors, and I want the derived things to also be enriched functors. Okay, so, all right. Now, okay, let's go back to our problem of trying to make different sets and different modules into monoidal closed categories. I proved a general proposition saying that if you start with a complete symmetric monoidal closed category, then its difference category is also monoidal closed. And as a corollary, different sets are indeed Cartesian closed, and also our modules for a difference ring R is also monoidal closed. However, you might ask, can you show us what exactly the internal Homs are? And indeed I can. It's actually very nice pictorially. So you consider the set of natural numbers with the successor function as a different set. Then the internal Hom between two different sets X and Y is the sigma set maps from n cross X to Y, or this is my preferred way of looking at it. Instead of single morphisms, I need to consider sequences Fi of morphisms between X and Y. So that they don't necessarily commute on the nose with the sigmas, but up to a shift. Okay? So you have an infinite diagram like this, where things commute up to a shift. Why is this? So what I want to create is a difference set. Why is this a difference set? Well, because you can have this shift map, which is similar to what Michael was talking about. It just shifts to the left and forgets the first entry. So with this shift, this is a difference set again, and this is the internal Hom in different sets. What you do for modules, well, you use the same kind of infinite ladder description, except you need to require that each of these levels is a homomorphism of underlying algebraic objects, so just a homomorphism of underlying modules. Okay. So our kind of guiding principle becomes that difference homological algebra must be developed in this framework of enriched category theory, where the relevant categories are going to be enriched over either different sets or, in the abelian context, over different abelian groups or different modules.
Can you remind us about this enriched business? Can I just point Can you remind us the definition of enriched category? I just thought because it's a crucial notion.
Yeah.
You didn't really say what's going on here.
So a normal category is a class of objects plus for every two objects you have a Hom set. An enriched category, so you fix yourself a V and some monoidal category, so V has to have a tensor on it, and this closed, well, it's best if it's monoidal closed, but it's not strictly necessary, but it has to have a tensor. So for any two, again you take a class of objects, but for any two objects, X and Y, you don't have a Hom set, but you have a Hom object, which is an object of V. Example that you fully well known, additive categories are categories enriched in abelian groups. You know, because the Hom set is not just a set, but also an abelian group. But luckily, you see, this is a concrete example, so an additive category is a category. But you could take some non-concrete category V, and then a V category is not a category at all.
Composition is just composition is.
Composition is a morphism from the. So okay, normally you would like to take F in here and G in here and compute F circle G, right? But you're forbidden from talking about elements in there. So these are just objects in an arbitrary category. So you have to say that composition is a morphism like that. Okay. Right. So if you look at these ladders and think of the shift operation, what are the sequences which are fixed under the shift? Well, if they're fixed, that means that F0 equals F1 equals F2 and so on. And that means that you have morphisms which actually commute with sigmas. So the fixed points of the internal Hom are the ordinary difference maps. So from this perspective, the kind of Ritz-style difference algebra is only the underlying category side of this enriched framework, and it only sees the tip of an iceberg. And the point is that, you see, when you're trying to develop homological algebra, the functor of fixed points is dangerous. It's not an exact functor. So if you take the fixed points too early, you're going to lose a whole lot of information. So the point is that somehow this has to be taken at the end when you're going to be deriving these functors. The derived functors of fix must also be taken into account. So somehow, otherwise you lose too much. All right, so okay, we now reach the liberation stage where we're rocking, and so now we're very open-minded. So note that different sets, which of course are the same as sets with an action of monoid n, or this functor category.
What is Bn supposed to be?
Bn is the, as I said, category of sets with an n action, with an action of the monoid n. So these are all equivalent categories, and this is actually a Grothendieck topos because the last description makes it a pre-sheaf category on this category
What
sigma.
does the dot mean here? Sigma dot S.
Dot?
Is there a comma or a dot?
Sigma.
Sigma
Here?
set.
Here?
Yeah, is that a comma?
It's a
That's
comma.
a comma,
Yeah.
sorry.
That's a functor category. It's functor category from the
Sorry.
little category I defined two sets. So, because it's a pre-sheaf category, it's a Grothendieck topos. And I will explain a little bit what this gives me. And moreover, you see difference rings, for example, can be viewed as ring objects in this topos. So I now place myself inside this universe, this new universe. So that
you assume your knowledge of what topos is by that audience here?
no, I will now. I will explain it on the next slide. Yes, but somehow this is a new universe, right? So this is the kind of Enriched point of view where I work with rings and then superimpose sigma on them from the outside. This is an internal point of view where I work in the new universe and I consider just normal rings in there. Now, okay, you might ask, of course, for modules, you get a similar thing. If you take a difference ring, that means that this pair of the kind of topos of sigma sets plus this ring is what people call a ringed topos. So this R mod, from kind of external point of view, is just modules in that ringed topos. Now, you might ask, all right, this is a trivial observation. Why are you telling us that? Well, this shift in perspective is actually important because now you can apply the full strength of topos theory and categorical logic to study these. And, you know, as you saw from these internal HOMs, they're not typically considered in the literature on difference algebra, and yet there's something very kind of crucial and important. So this you immediately kind of unravel, and many other things. So, okay, so our updated basic principle of what difference algebra is the study of algebraic objects internal to this topos of different sets. So, from categorical logic point of view, groups, rings, modules, they're all so-called algebraic theories, which are the simplest kind of theories, and it's very good to know that these are kind of models of these very easy to work with theories. And then you can, as I already said, you can apply the full power of topos theory and categorical logic, where people have a huge amount of theory for building mathematics. And then the enriched structure, when you view difference algebra like this, the enriched structure I discussed is automatic. All right, so let me tell you a little bit what toposes are. So a category E is an elementary topos if it has finite limits. So, you know, fiber products and a terminal object E. It's Cartesian closed, this I already explained. And then it has a subobject classifier. I think it's probably best not to try to read, I mean, you can if you like, but when I first saw this definition, it didn't really mean much to me. But let me explain a subobject classifier through examples. In the category of sets, a subobject classifier is just a two-element set, 0, 1. And it's useful for expressing characteristic functions of subsets. Right? So if you take a set X and a subset Y, you can write the 0, 1 valued characteristic function of Y inside X. So this is all I'm saying here. Let me show you what the subobject classifier is in the category of different sets. So this is the set of natural numbers union infinity with the following different structure. 0 goes to 0, infinity goes to infinity, and then I plus 1 goes to I when I is a natural number. And if you now take a difference set X and a difference subset Y, the characteristic function, which is now omega valued, for an element of x, you take the minimum n such that sigma to the n falls into y. Of course, if such an n doesn't exist, then it's infinity. And of course, y is then the pre-image of 0. It's the set of zeros of the characteristic function. So, in fact, the truth value here is 0. And the kind of false is infinity. Now, in any topos, this subobject classifier actually serves as an object of truth values for the internal logic of that topos. So let me show you what this logic looks like in different sets. So true is 0, false is infinity, and of I and j is the maximum, or is the minimum. Of course, the order is reversed natural order. Not of I is 0 if I is infinity, and infinity if I is a natural number. And then you have this implication here. Now, a word of warning is that the double negation is not identity. So this is not a Boolean topos, and it may be tricky to prove things. You're only allowed to use kind of intuitionistic reasoning, and you can't do kind of proofs that we'll love and use on a regular basis. So, okay, now we reach the enlightenment stage.
Is it New York? We're in New York.
So
It's like the Harry Bristol people have gone now. The Harry Bristol people got everything.
Yes.
okay, so topos theory philosophy. There's a general philosophy in topos theory which says that you see, usual mathematics is developed in the universe of sets. Groups and rings and so on are first of all sets plus additional structure. Okay, and topos theory philosophy says that you can in fact place yourself in an arbitrary topos and use that as a universe for developing very large chunks of mathematics. So an arbitrary topos can serve as a universe for developing a lot of mathematics. That's somehow the guiding logic. And then we can now using this guiding principle, we can now proclaim that difference algebraic geometry is in fact algebraic geometry over the base topos difference sets. Now, this base topos phrase is actually a technical expression, and there's a lot of machinery for working in this relative context over a base topos. So let me now try to illustrate that by defining different schemes. So Monique Hakim was a student of Grothendieck, and she wrote this monograph for developing algebraic geometry relative to a base topos.
In a base topos.
Over. So it's always like something, you fix your base topos S, and every other topos you obtain must be above it, like by a geometric.
Yeah, but in the case when S is sets, what are you talking about?
Then you just get so this construction here will just give you the usual spectrum.
Yeah.
Okay?
But you're working in the category sets. I don't know, what is relative business? I don't know what you mean. In the category sets.
So, okay, I mean, when you take a ring, then set A is a ringed topos, and then this spec ZAR. Nobody thinks of it as a geometric morphism to set A again, because this is sort of a trivial business, right? This is usually omitted. But in fact, it's a topos over the one you started with.
So set A is what?
Set A is a ringed topos. Set is a trivial topos. A is a ring object in it. Okay? So it's just that people normally, because set is a terminal topos, so everything maps to it. So usually this is omitted. But when you work in something like sigma sets, then it's kind of crucial that you have this geometric morphism into it. So this Zariski spectrum, you start with a ringed topos, which just means you have a ring object, and this produces a locally ringed topos, which means that this ring living on it is going to be local in the internal logic of that topos. This kind of boils down to saying that fibers, that kind of stalks of this will be local rings. All right, so I propose to use this general principle in our case. So if you take a difference ring A, this means that you have a ringed topos, sigma set A, and you can create a locally ringed topos out of that. So this is for the affine case. Hakim also gives a technology to talk about arbitrary relative schemes, and it's done through the machinery of stacks. Okay, we can go even further. She develops the notion of the étale spectrum. So when you start with a locally ringed topos, like we created on the previous slide, you can produce this spec et, which is a strictly locally ringed topos. So strictly refers to the notion of strict tensillization. And so that is going to give you the étale site and étale topos. And I propose to define the étale topos of a different scheme through this general principle. Of course, this guides me immediately to the definitions of several key objects. So, I've been thinking a long time on how to properly define the étale fundamental group, and what was bugging me for a long time is how to introduce some intrinsic topology on it, because, okay, the special case of the fundamental group is Galois theory. So imagine you have a difference field, and you're trying to define what it means to have the, maybe you take the some algebraic extension of it, which is a difference field extension, and you want to view this group. Now, there should be some topology on this group. Okay, in the classical Galois theory,
What group? So what group you do?
the Galois group.
So you have a difference.
So K sigma,
Yeah.
and you have L sigma. Okay, this could be possibly an infinite extension.
Algebraic extension.
Yeah, infinite algebraic extension. For ordinary fields, this Galois group is given the profinite topology, okay? Because you can look at finite stages in the extensions, right? But in difference algebra, what's been bugging me for a very long time is that a difference field might not have finite extensions which are closed under sigma. So the basic steps are finitely sigma generated, right? Now, should these be considered discrete groups? I mean, the Galois groups of those, should they be considered discrete or should they be given topology? And so this was bugging me for a really long time, and now I finally understand it through this setup. So the claim is that when you take this étale site of a different scheme, you can use the existing machinery from topos theory, which can calculate these relative fundamental groups by a certain type of geometric morphism. And the group actually is a pro-localic group inside here. So what does that mean? It means it's a projective limit of localic groups. So locales are sort of pointless replacements for topological spaces, which can be internally defined in this topos. So you're going to get some kind of topology there. And so this is the solution to the problem that I've been having for a long time, how to topologize these Galois groups. Okay.
So what does it mean concretely in the case of the Galois group?
You can, well, I'm not sure, how much time do I have? We can talk.
15.
15? So you can define something like compact open topology. So you see, the Galois group is, of course, in my case, not going to have just the morphisms which commute with sigma. That's too small, right? So what I'm going to have, so k sigma, and then you take this L sigma, and I'll be looking at this internal automorphisms of L over K, and I'll define the base sub-bases.
Internal to what?
These are, I defined this. These are internal HOMs.
Oh.
In the category of, say, K algebras. So these are these infinite ladders. And sub-bases for topology are sets, say, A, B, N, which okay, so you look at for sub-bases for topology, you look at those Fs which satisfy the property Fn of A equals B. Okay? So this is a little bit like compact open topology, where I put discrete topology on L, but it's just kind of slightly embellished to account for this N. Okay. So so this is what Galois theory looks like, just for difference fields.
So what happens now? You have a notion of strict tensillization for the field, and that should be trivial. And of course, the other definition of fundamental group refers to maps into that algebraic closure, fixing the base point.
Yeah.
Can you translate this into that kind of thing?
Yeah, so here it would be basically what you're probably referring to is that I should take, for the absolute Galois group, I should take the separable closure of K.
No, the difference closure.
Yeah, yeah.
Strict cancellation.
Yeah, but the separable closure, you can always extend the difference operator to the separable closure of a field.
However,
However,
in topos-theoretic terms. Is
yeah,
that-
in
is that
Tapas,
right?
yes, yes. On the other hand, this is not, it's not fully right, because this is just somehow the connected part of the. Okay, this picture is just for Galois theory of difference field extensions. If you ask me what is the absolute Galois group of a difference field, then this is not it. You have to allow, you see, you have to allow coverings which are disconnected but have sigma which shuffles the components. And even for a base which is a field, you get enormous complexity. So Michael and I encountered these examples in yet unpublished work, where you get somehow Cantor sets, topologically they're Cantor sets, totally disconnected, and yet they are sigma connected. And the flavor of the fundamental group, even for a field, is actually going to be a mixture of this type of Galois groups, which are kind of connected theory, familiar to us all, and some kind of automorphism groups of trees which permute all these components in a sort of wild way. So what I'm proposing for the fundamental group, even of a spectrum of a difference field, is really big. Okay? But the point is that you get, if you take only those morphisms which commute with sigmas, you get a very small group, and it doesn't have transitive actions on interesting objects. Whereas here, I'm getting the type of, the resulting group is a difference group, and it's acting on a difference object in such a way that, say, g dot sigma, sigma of g dot sigma is g sigma, sigma x. Okay? So you have this sort of difference group action on a difference object. This is the kind of the flavor of the theory. All right, in a similar way, you just you can now talk about difference total cohomology, which again I've been thinking about how to define for a very long time, but it always felt a little bit. The reason why I didn't publicize it is it always felt a little bit ad hoc and guesswork. Whereas now it feels very comfortable because it's an instance of a topos cohomology theory, which makes you feel kind of in a known framework and slightly safer. So what is it going to be? If you take this, so a different scheme, and you take a module for the strictly local ring, for the étale topology, then you can talk about étale cohomology groups of this module, which are basically kind of enriched derived functors of this structure functor. And because this functor ends up in sigma set, these groups are going to be difference groups. If you'd like to go all the way and obtain some actual groups, you need to continue this with the fix functor, the fixed point functor, and then compute the resulting cohomology as a composite of two functors. Okay.
With the Hawkes spectral sequence.
Yeah, with the Which one is the the Grothendieck spectral sequence for the composite? Yeah, yeah, for the composite of two functors. Yes. Okay, so some calculations with Michael. We were thinking for a while about how to define cohomology of difference algebraic groups, and whether you can apply this theory to sort of treat the families of twisted groups of Lie type as difference group schemes. And then if time permitting, the computation of X of modules over skew polynomial rings, for me it feels like it's an interesting result, very close to old classical results, but somehow very, very explicit. So, all right, so what for us are group functors, difference group functors. So we fix a base difference ring K, and then K difference group functor is just a functor from K algebras to groups. So this is the kind of base level. This is very kind of reminiscent to what people normally do. A difference algebraic group is such a functor which happens to be representable by a difference half algebra. In other words, the points in an arbitrary difference algebra R are just K algebra morphisms from A to R. Now, this is somehow not enough to see the full picture. You need to do the enriched versions of these, but I don't want to go into the details. And so for a difference group functor, a difference ring functor, and a module, GO module, we defined Hochschild cohomology groups, which is very kind of standard. You just treat these things as presheaves, and there are kind of classical definitions for this. But the point is that we can do it even in the enriched setting. Okay. And somehow these are able to see a lot more than these. Okay, and of course we give some spectral sequences connecting the two. And if you looked at Piotr's paper, some of these spectral sequences look very much like his.
With the joint paper, there was a joint paper.
Yeah, Piotr and another. Okay, so thank you. I took it on board. So, all right. So, how do we treat twisted groups of Lie type as difference group schemes? Well, look at this difference group scheme, SUN. So for an algebra R, it just gives you matrices from SLNR which satisfy this difference equation. So that's what makes it a difference group functor. It acts naturally on its Lie algebra through the adjoint representation. And note that when you evaluate this difference group functor on the algebraic closure of a finite field with the Q power of Frobenius, you get what people in finite group theory call the actual SU and Q. And apart from the kind of trivial case of SU2, we get that in characteristic 3, SU3, the cohomology is one-dimensional. So the flavor of these computations is, there are papers computing cohomologies for these groups, and they describe what happens as Q varies. And usually you have a generic predominant behavior. So sometimes, on finitely many Qs, you get a different behavior, but for the generic case, you get that they're one-dimensional. So this is what our technology can capture. And similarly, we did also the Suzuki difference group scheme. So the symplectic 4 group has an algebraic endomorphism whose square is Frobenius. And then you can write this Suzuki difference group scheme, and it naturally acts on this submodule of R4. And when you evaluate this group scheme on the Q Frobenius, you get an actual Suzuki group. And again, we can compute these cohomologies. Okay, so maybe that's a good place to stop. Thank you very much for listening.
Do you have copies of notes on the difference group schemes? Work with Michael. Do you have? Is it written up?
It's in progress. Hopefully by the end of the week we can...
End of the week.
Well, maybe not.
So let me ask about my favorite. Let's talk about torsors for GM. H1 GM should be like line bundles. So what's the setting in this case? What happens?
So yeah, we also have results for diagonalizable groups. So different subgroups of GM, and the result is that their cohomology vanishes for. So if you take some specific modules, some kind of finite dimensional difference modules, then the cohomology vanishes. So it's almost like a beginning of being able to say that they're linearly reductive.
Well, I'm on GM units. What happens then? And of course, I know first you have to translate it into a statement about
Yeah.
difference group somehow. But if that's part of the geometry, the difference algebraic geometry, you should be able to say something about torsors for the ring.
Yeah, I don't know. We didn't do this. I think we do have some calculation, but yeah, maybe I can talk to you later about. I think I can dig out some calculation, like some explicit.
I notice all your groups are affine. Do you have any results on groups not attached to algebras?
Well,
Like abelian variety, an analog.
yeah, we didn't look at that, and that's more difficult in the.
Has anybody in this context looked at that?
I don't think so.
Okay.
Well, there are some model theoretic results
In
on,
terms of what the groups are in different fields.
yeah,
Just kind of
but not on
cohomological
cohomologies.
work.
Yeah.
No.
Also, I'm not clear on what difference field extensions give you a Galois theory. So
well,
every difference field
For
extension?
example, in this case, L is an algebraic extension of.
It's what?
Algebraic.
Algebraic extensions. Every algebraic extension?
Not every. You have to have
That's also a difference.
the ability to lift the sigma on it.
Yeah,
Yes.
sure. Oh, okay.
So you can always go to the separable closure, but it's a very interesting problem whether between K and its separable closure, whether there are some finitely dimensional extensions, and that's sometimes it doesn't.
Right.
Yeah, sometimes you can't find it. And but
Is
this
there
is.
any similarity between this Galois theory, anything we could get our hands on, sort of anybody's used to differential Galois theory?
Well, there is in Cohn's book. There's this flavor of Galois theory that I'm talking about here. There's this flavor
Very
at the end of this book somewhere. Yeah,
Because I was
but
thinking, in differential Galois theory, we, unless we put special conditions on the constants of the ground field, we don't have enough automorphisms that commute with the operators. But in this case, if you put special conditions on something to do with the ground field, can you possibly?
But this is not the same flavor
It's
of
not the same
Yeah,
flavor.
so this is not the Galois theory of linear difference equations.
Also, in differential context, take an algebraic extension, then you, that's all you've got because you can use with derivation, right?
Right, I wouldn't take an algebraic.
Yes, no, but he's doing algebraic extension.
I know, but that's what he has to do.
That's what he's actually. Yeah, you're not doing linear difference.
No, it's not Picard-Bessio flavor.
Galois theory.
Yeah, no.
In the sense, no, he's not.
Yeah, it's not Picard-Bessio.
And your Galois groups are not different schemes.
It's just.
They're not.
It's just the fact that
Is that true?
the usual profile like Galois, you have to do something else because sigma's operating. That's all. you
They're
have
not
to
in
do.
a category
Yeah.
of different schemes. No. So that's strange.
Yeah, I don't understand the question. So,
What are your groups, in differential Galois theory, the groups are actually differential algebraic groups.
He's just doing
but
algebraic
no,
extension.
this is going to
But
be,
no.
yeah, this is just going to be some
Different cup of tea.
difference group, but it's not difference algebraic group. It's not a Picard-Bessio style theory.
Right.
It's
Yes. And I know, have you looked at all at the differential algebraic geometry case? Is there a need for this sort of structure?
so-
to get
so of
your
course you can,
homological algebra?
you can do a lot of things in the same flavor. So the internal HOMs for differential case do not need enriching because they, it just if you say consider the combined differential case, then the internal HOMs are going to be kind of bigger because of the difference perspective, but not because of the differential one. So I think you could do a lot in the mixed case, and in fact,
Differential.
yeah, I think you can repeat a lot of this stuff, and I intend to give this to one of my students.
Good.
Let's end speaker again and continue with the